Welcome back. I'm here with another lecture from organic chemistry, and I hope you had a great time until now. In this lecture, I'm going to go through three terms. The first term that will be radioselectivity, and the second, and stereoselectivity, and the third one. When do we say this reaction is stereospecific? Okay, and the cartoons that you see in front of you on the left side, it says we have a reactant that is producing two products, and the reaction is favoring one of the product. Okay, so the reaction is favoring one of the product. It says we have a stereoselectivity. On the right side, it depends to the stereospecificity of the starting compound, whether it's say it's R or S. You will get a specific product. Okay, you're not gonna get both of them. Only one of them will be possible. In that case, we say the reaction is going to be a stereospecific. Okay, let me practice some example about each of these terms, and maybe that one is going to help you to understand what's the meaning of radioselectivity, stereoselectivity, and stereospecificity. Okay, the first one, and radioselectivity, we have an alkyl halide, and the alkyl halide we're going to treat it with a strong base, and so the reaction will go under E2. Okay, say we are dealing with E2, and this is going to be our base ethoxide. Okay, is paired with sodium. Sodium will have a positive charge, so this one will have negative charge. Okay, and of course you can write this one. You can write it as just simply say ETO, and then say sodium close to it. Clearly, sodium will have a positive charge, and this one will have negative charge. Okay, we have alpha carbon. Where is the alpha carbon? This is the alpha carbon, and we have two betas. This is beta 1, and that one it will be beta 2. And depends from where we remove the hydrogen, we get two products. If we remove one from beta 1, so let's say we removed it from beta 1, product that we will get, it will be this. So we will have a double bond here, double bond it will be there. And so I'm going to highlight the double bond. Okay, the double bond, it has two hydrogen attached to it. So those are the two hydrogens. And this one, it has technically less substituent, and we said the product, we called it is a Hofmann's product. Okay. Next, if we take the hydrogen from say beta 2, and in that case we will get such a chemical compound. Now we will have double bond. The double bond is going to be somewhere there. So let's highlight the double bond. Okay. Our double bond, it has more substituent. It has two methyl groups. Used to be two hydrogens. Okay, two hydrogen, one end, and then we have an ethyl with hydrogen. So there, in this position, forgive me, in this position we have hydrogen. So technically, three of the substituents are hydrogen. But in this case, we'll have only two hydrogens and two methyl groups. So the second one, it has more substituent around the double bond, and we say this one it will be the so product, and thermodynamically this product is more favored, and so we said this product will be the major one. Okay, this product is favored and is more stable, and so you get more from the so product. Okay, now the reaction is favoring one specific carbon, or how about this? A specific reaction is favoring specific region. Okay, a region, and which region is favoring this carbon? Okay, I'm going to highlight that carbon. So the reaction is favoring this position, beta 2 instead of beta 1, and we see the double bond between alpha carbon and beta 2 instead of beta 1. If that's the case, we say we have a preference for a specific region. Okay, and this is going to be radioselectivity. So position of the double bond is changing, and is it fair to say the connectivity here is changing? Yes, the connectivity is changing. Be careful. Okay, the connectivity is changing. Double bond used to be terminal, now between the two methyl substituents. How about stereoselectivity? Stereoselectivity, I have such a compound, and this compound it has bromide. Here, the bromide is sitting on the alpha carbon, and we have only one beta carbon with hydrogen, and that's going to be here. Okay, and why the second one is not helping us? This carbon, it has a methyl substituent, so it doesn't have hydrogen, and it's not going to help us with E2 reaction. So if we want to do E2 reaction, okay, let's say we want to do E2 reaction, and again, our base, let's go with sodium or sodium ethoxide. Okay, sodium ethoxide, and this reaction is going to go through E2. Okay, but you have to ask yourself, okay, from where I should take the hydrogen. I have only one option, and it's going to be the beta that I have it with a blue color. Okay, now let's draw the conformation, the numerical projection of this molecule. And in one case, okay, and this carbon, that one I'm going to highlight, the yellow carbon. Okay, that's I'm writing with a black color. I have tertiary butyl, bromide, and hydrogen. You can put them wherever you want. It doesn't matter. Okay, that's going to be my front carbon. Okay, so I'm looking to the system through this direction, and so I see hydrogen, bromide, and a tertiary butyl. Okay, again, distribute them wherever you want. And on the back, I see 2 hydrogens and 1 methyl. Okay, 2 hydrogen, 1 methyl. In order to run E2 reactions, I need to have one of the hydrogen to be in anti-position relative to the leaving group. So keep one of the hydrogen in anti-position under any condition. Wherever you put them, it doesn't matter. If you want to do E2 reaction, hydrogen must be in anti-position. Now, okay, I'm left with 2 position for the methyl. Methyl, it can be on the left side or on the right side. So in one case, I put it on the left. Second case, I put it on the right side. Now, the one on the left, okay, if you look at the one on the left, the tertiary butyl versus the methyl, the 2 largest group on each carbon, on carbon alpha and carbon beta, you see they are in anti-position. Okay, so they are in anti-position. Okay, and again, I'm gonna keep the bromide and hydrogen in anti-position. And now I look to the methyl versus tertiary butyl. This time, the bond angle between the dihedral angle between them is a 60 degree. So these 2 are in a gouge position. But okay, which one of this is more stable? Clearly the one that's on the left. Why? Because the tertiary butyl is way far from methyl, and the steric effect between them is minimum. Okay, so the left side is more stable than the right side. Okay, now let's introduce a base. Okay, again, remember that. Okay, you have hydrogen there, and also you have leaving group this position. The base or tertiary butyl or ethoxide, the ethoxide is going to go after this hydrogen. Again, ethoxide is going to go after this hydrogen. So what will happen? They will remove that hydrogen, and at the end, the bromide will take these 2 electrons, and it will leave the system. Okay, so I'm going to highlight those. Okay, so let's put the line here. These 2, they will be gone. Okay, now if I take those 2 out of the system, what do I get? Okay, on the left side, I see these 2 group on one side. And on the right side, I see tertiary butyl and hydrogen on one side, and other side, I see hydrogen number 1 and methyl on one side. Okay, the front carbon, it has the front carbon that we wrote it with a blue color. It has tertiary butyl and hydrogen number 1. Okay, so I have carbon number 1. Okay, carbon number 1. It has tertiary butyl attached to it. Okay, and what else? It has hydrogen number 1 also attached to it. Okay, and carbon that is back, and we wrote it with a blue color. Okay, so the carbon that is back, okay, and we wrote it with blue color. I'm talking about the substituent, and it has methyl and hydrogen. And which hydrogen? This hydrogen and the methyl. Okay, remember we said this hydrogen is in the same side with tertiary butyl. Tertiary butyl. Where is the tertiary butyl? Put hydrogen in the same side. So I'm going to put hydrogen here, and then methyl, it will be there. Okay, now of course we have a double bond, so let's put the double bond there. Okay, this is going to be the first priority, and that one, it will be the first priority here. Okay, or you can say this one technically is a trans. Okay, and if I run the same reaction with the gouge one, the gouge one is going to give me this. It's going to give me 2 carbons attached through a double bond. I will have the tertiary butyl with the methyl on one side. So on first carbon, we know we have tertiary butyl and hydrogen, but then the methyl will be on the same side with the tertiary butyl, and hydrogen will be there. Okay, this time the 2 substituents are on the same side, so I'm gonna say I got cis. Okay, now which one of this is more stable? Let's go back to the starting point. We had anti versus gouge. Anti is more stable, than gouge. So what does it mean? It means the cis product will be less stable than the trans. Trans is more stable than cis product. And so the reaction is going to favor the trans. Okay, so in this case, I started here. I started with technically anti and Gauch conformation, and the reaction is favoring. A reaction is favoring one of the product, the trans versus the cis. Trans is favored. In this case, we say we have stereo selectivity. Reaction favored the trans versus cis. Remember, we started from same product, same same substrate. Okay, from same substrate, but we got two different products, and one of them is major. Which one? The trans one. Okay. Now, how about the stereo specificity? Stereo specificity, I have R and R, and next molecule, I just simply change position of these two substituents. Okay, I switch position of phenyl with hydrogen. If you flip them, clearly the configuration it will be opposite. From R, it will turn to cis. Now, if I treat them with again same base, okay, to do E2 elimination, I want to do E2 elimination. A product that I will get. Okay, of course, this one, it will be gone, and hydrogen as well. Now, look to that pink or, like, I don't know, say reddish color that you see. The group that on one side of it, they fall on one side, those two, give me. Those two, you will write them on one side of the double bond, and you keep these two on the same side. Okay, so what do we get here? We will have double bond, carbon-carbon, double bond, and one side we will have phenyl. Okay, and then blue one, it will be here, the back one. And where is the methyl? Methyl is going to be here, CH3, and hydrogen, it will be here. Okay, this is the first priority, and that one is the first priority. So this one, it will be Z isomer. Okay, and if we run this, okay, for the second molecule, and we're going to get this. We're going to get, again, we have carbon attached to another carbon through a double bond. And what do we have? The front hydrogen, we have the front carbon, we have hydrogen. And what else? We have a phenyl down there. And the blue phenyl, it will be on the same side with hydrogen. And the methyl, it will be on the same side with the phenyl. Okay, which phenyl? The phenyl that it has green color. Okay, so, and I'm talking about this. These two, they will be on the same side. Okay, same side. And so this is going to be number one, and that one, it will be number one, and this is going to be E isomer. Okay, so I got two configuration, and Z and E. Okay, I want to talk about the starting compound. What's the relationship between the starting compound? In the first one, we have R and R, and this molecule is R and S. Okay, one of the stereo centers got flipped, while the first one stayed as it is. So starting molecules are diastereomers. Okay, diastereomers. What should I call the product? The product, I got Z and E. And these two also, they will be diastereomer. Okay, diastereomer. So the stereo-specific reaction is a reaction that is going to hold the relationship that we have between the starting reactant. If they are an enantiomer, you will get a product that they are an enantiomer. If you start with diastereomer, the product also will be diastereomer. And in that case, we say we have a stereo specificity for the reaction. Okay, we said in order to have elimination, we need to have hydrogen in the beta hydrogen on a beta carbon that is in anti-position relative to the leaving group. Otherwise, we can't remove hydrogen, or we will not have E2 elimination. So in this case, if I take this hydrogen, okay, this hydrogen, as you see, is in anti-position with the bromide, and what do I get? And the product that I get is going to be 1 and 2. Here, 1 and 1. This is going to be E. Okay. Well, the Z, we cannot get it. Why we cannot get it? Because in any way, okay, in any way you technically here, in any way you rotate, okay, you rotate it like you rotate the molecule, and then like the bromide and hydrogen, they will not be in a position to give you, to give you technically the E isomer. Okay, let me practice this one for you here, and so. I have the bromide up. I'm going to write the bromide here. This is the bromide. And then, okay, what else? We have hydrogen here and tertiary butyl there. And next, we have phenyl in this position. Methyl is going to be here, and hydrogen is going to be there. Okay. Now, if you remove these two, you will get this. You will get the carbon. There's a double bond. On the front carbon, what do we have? Okay. We have tertiary butyl. And okay. And what else? Also, we have so we have tertiary butyl, and tertiary butyl is going to be on the same side with the methyl. So we have methyl is going to be here, and next, and the phenyl is going to fall here, and hydrogen is going to fall there. This is going to be the first priority, and this one will be the first priority. So that's going to be the E isomer. Okay. Now I have two molecules here that is asking me why the first reaction is slow while the second one is faster. Let's go through these two, and we're going to finish the lecture. Okay, so the first one will be cis. Okay, I have two groups that are pointing in the same direction, and this is the alpha carbon. That one is the beta carbon. And remember, I need in order to do E2 elimination, I need to have hydrogen that is in a anti-position relative to the halide. Okay, where can I find that? Where can I find the hydrogen? Okay, I can find hydrogen here. Okay, I can have hydrogen here. This is a beta carbon, and that hydrogen is pointing down. Okay, so hydrogen is pointing down, and it's way far from, like it's opposite of tertiary butyl, which is a bulky group. Also, I have hydrogen that is here. Okay, that hydrogen also is pointing down. So I have two hydrogen. Remember, that one also is beta. Okay, so technically I can get two products. And one of the products, if we go with beta 1 versus beta 2, beta 1, it will give us such a product. Okay, so we will have double bond here. Okay, and if we go with beta 2, so this one from beta 1, and if we go with beta 2, the product we get, it will be such a thing. Okay, we have the tertiary butyl here. Okay, and the double bond is going to be there. Okay, and again, and just to here show you that tertiary butyl did not change. So maybe I should just draw this one as pointing up. Okay, now which one is more stable? This one is more stable. Why? Because it has more substituent. Oh, that one, it has just technically two hydrogens and also two carbons. So the one that's from beta 2, beta 1. Okay, beta 1 is more stable than a product of beta 2. Okay, this, like in this molecule, it has two hydrogen that can be target. And I said the beta 1 is more favored than beta 2. Okay, what if they are in a transposition? Okay, if they are in transposition, we're going to have an issue. Okay, only hydrogen that we can eliminate, it will be this hydrogen. Okay, well, because that hydrogen is pointing up, similar to tertiary butyl, and this one is in beta position. Okay, and this one is beta 1, beta 2. In this case, if you call this one beta 2, this one is not going to be helpful. Okay, because the tertiary butyl is pointing up. But we have an issue, and what's the issue? Each of this carbon, it has three hydrogens, and those three hydrogens are going to create steric effect. So when the base try to reach this hydrogen from the top, it's gonna sense the tertiary butyl, and that's gonna have a huge steric effect. Okay, so why this reaction is a slow reaction? Because of the tertiary butyl. We can reach it only from the top, while the tertiary butyl is pointing up, and we can have only one product, and this is going to be our product. Okay, so if this one is, let's say, is pointing up, and then we will have the double bond here. That's the only product that we can technically have. And again, why slow? Because the tertiary butyl is pointing up. And this is going to be the end of this lecture. And thank you very much.